We're working with topic 5.10 and 5.11, which is optimization. And optimization problems are nothing more than max and min problems. All right? They're max and min problems, and we just have to apply them into a word problem setting. This is the classic, one of the classic max and min optimization problems. You want to enclose a garden with fencing to keep the rabbits away. Good luck with that. A shed will serve as the boundary for one side, so we're going to have a building on one side, and fencing is needed for the other three sides. All right? So this up here is my building. Okay? If you have 60 feet of fencing, what is the area of the largest garden you can enclose? All right? Largest points to what that we've been studying? Some type of maximum, right? So if I call the width x, and it doesn't really matter, which way that we do this. If I call the width x, let's say, then this over here is x. Now we want to stick with one variable, of course. So let's think about this. X plus x is going to be 2x. Right? Those two we know are the same. What's left for this? Isn't it just 60 minus 2x? Right? And we're asking for the area of the largest garden you can enclose. Well, area is just length times width. So my length is 60 minus 2x. My width is 2x, and now I've got a function, a of x. Got a function. And that function is representing the area of this in here. It's representing that area. We want the biggest one that we can get. So this is just a maximum and minimum problem. All right, this is just an extrema problem like we've been working on. So let's distribute this 2x. So a of x equals 120x minus 4x squared. And there's my function, and it looks a little bit better now. And what do we normally do? We take the derivative, we set it equal to 0. So a prime of x is going to be 120 minus 8x. We set that equal to 0. To find critical points like we always do. So 8x equals 120. We divide both sides by 8, right? And I believe that's 15, isn't it? 120, double check, divided by 8 is 15. So 15 is a place where the slope of the tangent line is 0. Now, this one's pretty easy. Isn't my original function just an upside-down parabola? If you know what function you're working with, I know that this thing is some kind of upside-down parabola. There's not much that can go wrong with this function. We don't need to spend a bunch of time on this one. Here's 15, okay? And we could apply the first derivative test, we could apply the second derivative test, we could apply all of our things to prove that this thing is the max. Okay, but you all are good at that at this point, but this is a pretty straightforward function. So when x is 15, all right, when x is 15, then we get my largest area, all right? And so we could then, now it specifically asks for what is that area. So I would need to put it back in here. So my width is 15, and my length is 60 minus 30, so that's 30. So my largest area would be 15 times 30, which is 450. All right, and we're talking about square feet. That is one of the classic optimization problems. Setting up a function and then working through it. Let's go to the next problem. This one is a little bit more detailed. We want to construct a box whose base is a square. All right, we want to construct a box. Already I'm thinking of a picture. Okay, the base is some kind of square. You know, however you want to draw your box, I drew it that way. Okay. Has a volume of 36 cubic feet. Volume is 36 cubic feet. Notice I'm pulling information out. All right. The material used to build the top and bottom costs $8 per square foot, and the material used to build the sides costs $6 a square foot. Determine the dimensions that will minimize the cost to build the box. All right. Well, the cost, okay, is going to equal 8 times what? Well, this is x and this is x, right? Because it's a square. We can call this y. All right. So the area of this bottom, isn't the area x squared? But I have two of them. So it's going to be 8 times 2x squared plus 6 times all of these 4 vertical sides here. And their area is xy, isn't it? So I have an xy here, I've got an xy, all the way around. I've got 4 of those. So that is going to be 4xy. All right. So we've now got 16x squared plus 24xy. Okay. Now, what I would do is we need to eliminate a variable. We need to eliminate a variable, and the best way to do that is to start with the relationship we've got. The volume of this thing is x squared y. Okay? The volume is x squared y. So I'm going to eliminate the y. We like working with x's. Okay? So my y value is, and didn't they tell me the volume was 36? Right? So this is going to be 36 over x squared. They told me that the volume is 36. So now I can bring that over here and eliminate this y, and I have 16x squared plus 24x times 36 over x squared. Cleaning that up, my cost is going to be 16x squared plus 24 times 36. That's not one that I normally do in my head. 864 over x. Okay. So what I would do at this point is what we always do. Now we have a function for the cost, and we're looking for the dimensions that would minimize the cost. I will tell you right now in these problems, the challenge is getting to this point right here. From that point on, most of the work should be straightforward. Finding the maximums and the minimums and so forth is not going to be that bad once you get a correct equation or function. All right? So continuing on, if I was doing this problem, I would probably, well, let's go ahead and take the derivative. Okay, so c prime of x is going to be 32x. This is like 864x to the negative 1. So this is going to be minus 864x to the negative 2. So we'll put that over x squared like that. Okay. And we could, at that point, set this thing equal to 0. I'm running out of space on this page, so let me add a new page here. We had 32x minus 864 over x squared, and we're going to set that equal to 0. Okay. And at this point, I would probably add this thing to both sides. So I have 32x equals 864 over x squared. I'd multiply both sides by x squared, and I have 32x cubed equals 864. So we've got 32x cubed minus 864 equals 0. I can pull out a 32, and I've got 32 times x cubed minus 27. And so my critical point, we'd finish this up, is going to be 3. Okay? Critical point there is going to be 3. So you can do a candidates test at this point. All right. This is some type of critical point on this function. All right. And what are my possibilities for this box? What are my possibilities for this box? Well, is 0 going to work? Can I do anything with 0? No, I mean, I need a base, right? So why not try 3? X equals 3 is a candidate. All right. And I could also now do a little bit of analysis to see, is this 3 a maximum or a minimum? Okay. And our other possibility is x equals 6. Why is that a possibility? Well, because the volume of this thing is 36. And if we think x times y, this base here cannot have anything bigger than 6, all right, or we're not going to get to 36. All right, so we can also check, we can check 3 and we can check 6. All right, and if we do a candidates test, we find out that this 3, all right, if I do a candidates test, C of 3 is 432, and C of 6 is 720. This is our minimum cost. You could also do some first derivative test. You could do some second derivative test with this thing to show that this thing is a min. All right, all those things are available to you. All right, I would be okay with you going into the first derivative test or the second derivative test, as well as looking at this one on the candidates test. All right. Here's a detail. This is just a detail of everything that we just went over. This problem: oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate. Underline that word, constant rate of 2,000 cubic centimeters per minute. Okay? A recovery device arrives on the scene and begins removing oil. The rate at which oil is removed. Rate points to a derivative. We are thinking a derivative here. All right? So if we call V our volume, we're thinking V prime of T. Okay? Well, it's increasing at a constant rate of 2,000. What's the derivative of 2,000x? What's the derivative of 2,000x? It's just 2,000. So we're going to have 2,000 minus this 400 square root of t on this problem. All right? And again, coming up with the function is the challenging place here, but that's why I made a big deal about this constant rate. Constant rate points to this 2,000. Okay? So here's my function. What do I do with it? I always set it equal to 0. And I start working through my critical point process. All right? So I have 400 square roots of t equals 2,000. The square root of t equals 5. And we can start working through our process for when it is a maximum volume. Once again, on these problems, the key is getting to my function the right way. And once you get to your function the right way, the process is everything we have done in Unit 5. And by the way, I have some detail of this problem listed for you here if you want to see the detail of finishing up that problem. We're going to stop there for today, and hopefully that helps on optimization.